factor comes into play when we talk about the quantitative, you already know the answer, quantitative version of solutions. Moles, if in doubt. Okay, so all solutions have two parts. They have solute and solvent. You can have multiple solutes, but only one solvent. Now, all the stuff I just mentioned a little while ago, air we're breathing, gold, a piece of jewelry, sugar and water, all of them have at least two parts, and they're homogeneic. In other words, we can't tell the difference between the nitrogen and oxygen in the air. When we mix up sugar and water, we can't tell where the sugar is and where the water is. And on your ring, it looks like it's all gold. No. The reason why they put copper in there is to make it stronger, because gold itself is very soft, wears very quickly. And at $5,000 an ounce, you want to keep it around as long as possible. Okay, so how do you tell the difference between solvent and solute? One is more than the other. So solvent is greater than 50%. The combination of solutes, whether it's 1 or 10, is less than 50%. So sugar and water. What would be the solvent? Water. If the sugar is the solvent, you got one crazy sweet drink. Did you know regular Coke or Mountain Dew, if you took a can, an empty can, and filled it 3/4 of the way with sugar, that's how much sugar is in a can Coke or Mountain Dew. Now, it's sweet, but it's not that sweet. You know what they do to counteract it? They add phosphoric acid. Acids are sour, so it counteracts the gross sugarness taste. Also, carbonic acid with carbon dioxide. Do you ever drink a flat Coke? It's awful. It is like drinking watered down syrup, you know. That's because the carbonic acid is gone. Oh, all right. So let's look at what's going on. Okay, so let's have a salt solution. So we're going to drop a cube of sodium chloride, table salt, into this water. So this is water. And we've got a cube of salt. Now, salt, as you all know, is sodium chloride. Now, this is what water looks like. And the thing about water, it's very, very, very polar because of the oxygen in there. Whenever you introduce oxygen to any compound, it makes it polar. So by being polar, certain parts of it take on a positive and that person that's in partial differential equations would know what that means. And another part is going to be partially negative. That's what a polar molecule looks like. It's not evenly distributed as far as charge goes. Now that charge is zero, but the distribution of the charge is not equal. So there's another phenomenon that I've mentioned before, but everything is in motion. No exceptions, unless the temperature is absolute zero, the minus 273 Celsius. So that means the water is moving. Salt crystals moving, not as much, but it's definitely moving. So what's going to happen is we're going to have these water molecules bump up against the salt crystal. Now remember, we've got a partial charge on that water. So what's going to happen, it's going to attract that negatively charged chloride part of the table salt. Equally so over here, that negatively charged oxygen is going to be attracted to the sodium ion. Now, because it's moving, that water is going to pull out the sodium and pull out the chloride. That's how the sodium salt dissolves. So, how can we speed that process up? Okay, stirring. Okay, there are three ways we can speed that process up. Okay, mechanical agitation or stirring, as she said. What else? What? Heat or thermal, as he said. Now, heat is just a manifestation of kinetic energy. Kinetic energy is the energy of motion. So when we raise the temperature, the motion of those particles increase. What happens when you are Italian? The motion of those particles increase. That means the odds of that water hitting the surface of the table salt increases. That's why heat speeds up dissolving. What about the last one? One more. Let me ask you this. If we have powdered sugar versus a big lump of a sugar crystal, which will dissolve quicker? Powdered sugar or the big lump of sugar? Everyone says powdered sugar. We're absolutely right. What's the difference between the two of them? Huh? Exactly. The powdered sugar has a tremendous amount of surface area compared to the rock candy kind of big lump of sugar. So surface area. These are all directly proportional to movement. In the case of surface area, it's also a phenomenon that happens only on the surface. So if you've got a sodium ion deep inside a crystal, that water cannot touch it until the surface is dissolved away. So by bringing that sodium ion closer to the surface, it'll happen faster. And that's what happens when we increase the surface area. So all of these contribute to motion. So if any of those go down, the motion goes down, hence the rate of dissolving goes down along with it. Now, does that make sense? All this while you were wondering why you stirred your coffee to get the sugar to boil. I know that was a question in the back of your mind. All right. Okay, so we have salt dissolved in water here. Let's have another beaker. With sand. The formula for sand is silicon oxide. It's also the formula for glass. Okay, so we put salt in water, heat it up, stir it, it all dissolves. We do the same thing with the sand in the water. Nothing happened. What's the difference? Huh? The salt was a solid when we put it in there as well. What does that mean, inert? Nothing happens to it. Yeah. Okay, so remember in the universe, we go from unstable to stable, all right? That must mean the sand in that water is more stable than the salt in that water is. So we have two factors that are kind of fighting each other, two forces. One is called the crystal lattice force. That's what keeps the crystal together. So we've got two competing forces, solvating force, crystal lattice force. If the crystal lattice force is stronger than the solvating force, like sand, it'll stay solid. If the solvating force is stronger, it'll dissolve. Now, one of these is a function of temperature. Which one do you think it is? Right, solvating. So that is function of temperature. That's why raising the temperature increases the solvating force power to overcome the crystal lattice force. And that's why something dissolves in water. Now, I kept bringing up sugar. Let me show you what sugar looks like. This is what glucose looks like. What do you notice on that glucose molecule? Lots of what? Lots of carbons, that's true. What else? OHs, just like water. There's an expression in everyday life called like dissolves like. So sugar is sort of like water. So it's like water because of all of its OHs. So sugar is very polar as well because of those oxygens on there. There's all different kinds of sugar. We just finished a carbohydrate unit in my other class, and there are about, I don't know, 40 or 50 different sugars, major ones. They're just all over the place. There's starch, there's cellulose, there's raffinose, stachanose, xylose. ribose, deoxyribose. They're just all over the place. Glucose, lactose, and go on and on and on. There's lots of them. And if you take 2B, M2B, you will get to learn all those. At least you learn them if you had me. So, okay. So that's why sugar dissolves well in water, because they're very much like one another. It's just like if you had, you just washed your car and you had to drive down a newly oiled street and you got all that oil back on your car. When you get home, the first thing you do is take your hose out and spray it down. What will not happen? Oil will stay on there because oil and water don't mix because they're not alike. Oil, it's got these big, long carbon chains that are totally nonpolar. I mean, they're long, really long, like 18 carbons long and longer. Water is this little bitty thing. Doesn't have carbons at all in there. So nonpolar, polar. That's why you've got to get something called soap to get rid of that oil in there. And the soap has got two parts to it. It's got a nonpolar part and a polar part. The polar part matches the water. The nonpolar part matches the oil. Just like when you wash dishes. Hot water works better than cold water because of the solvating force. And also you've got soap. This plain hot water does a poor job of removing grease. Soap in there does a good job. Why? Because soap has got a polar and a nonpolar part. Polar for the water, nonpolar parts for the grease. They're also called surfactants. They're also called emulsifiers. And they're also called soap. All three of those are the same thing. Different forms, but same thing. Okay. On your test, guaranteed, you'll have this question. I'm going to ask you to describe how a table salt crystal dissolves in water and what are the factors affecting its dissolving. That has been on every test I've given on solutions for the last 22 years. Okay.
Can you say it one more time? What easier?
Yeah, how does a table salt crystal dissolve in water? And what are the factors that affect its dissolving? The mechanical agitation, the temperature, and then the surface rate. Okay, so that's your introduction to solution. Now, this is a qualitative one. Next week, we're going to get into the quantified side of it. Good old moles per liter. Now, this liter is liquid liters, not gaseous liters. They're not the same at all. They're entirely different. Gaseous liters is 22.4 liters per mole. Now, those of you who have Saturday lab, probably most of you in here, you'll notice on some of the bottles, the liquid bottles, you'll see a big M. That's solution concentration. I'm going to talk about that in extreme detail next time we meet. I mean, next time we meet, we're talking about double replacement. But the Saturday, a week from today, talking big time about molarity. Okay, so that's what I wanted to do today is introduce you to solutions. So we are done for today.
Mm-hmm.